And same, if V goes up and P stays constant, T, yada, yada, yada. Good. Next passage. A class is giving a demonstration of solution chemistry and solubility equilibria. A 6.57 gram sample of nickel SO4 complex with 6 water molecules with a molar mass of 262.84 is dissolved in enough water to make 50 milliliters of a green solution and 7.15 grams of a Na2CO3 sodium bicarbonate complex with 10 water molecules, which has a molar mass of 286.14. This is dissolved in enough water to make 50 milliliters of a colorless solution. The two solutions are mixed and a green precipitate forms. The resulting slurry is divided into 2 equal portions. To one portion is added an excess of 6 molality of hydrogen chloride, which results in the disappearance of the precipitate and rapid evolution of the gas. To the second portion is added a few milliliters of 6 molar NH3. I may have incorrectly said molality. 6 molar hydrochloric acid, 6 molar NH3. The precipitate dissolves and a blue solution forms. How many sodium ions are in the initial 50 milliliter solution? So, well, let's immediately look at the answers and see that they're on the order of Avogadro's number, right? 10 to the 22 to 3. So I imagine I'm going to be remembering the number, Avogadro's number. 2 seconds. 6.022 times 10 to the 23rd. So there is 6.022 times 10 to the 23rd moles, or molecules of sodium bicarbonate in 1 mole of that. So if I imagine the initial 50 milliliter solution of Na2CO3 has 7.15 grams of the complex with a molar mass of 286.14. The grams, so I'm going to use dimensional analysis here, and I'm going to say it in words and then assume that the math checks out without actually working it through. But let's go 7.15 grams times 286.14 grams per mole. So I actually want to invert that. So I want to say 7.15 grams times 1 over 286.14, which means moles per gram. The grams cancel, which leaves me with whatever the amount is of moles. Then if I multiply that by Avogadro's number, I will get that many number of molecules per mole. The moles will cancel out, and I'll be left with the number of molecules I have. Now, note that the number of sodium ions, I should have 2 sodium ions, right? Because there's 2 sodium ions, I will imagine that I have to double my answer. So once I do a calculation like what I said, then I have to also multiply by 2. And I'm just making sure that, right, multiplication can be done in order. It's commutative. So yes, so you take that number and you multiply it by Avogadro's, and we'll get roughly 3 times 10 to the 23rd, or 22nd, ions. Cool. If red litmus paper is dipped into sodium bicarbonate solution, it will red litmus paper turns blue in the presence of a base. The carbonic acid you know what, I'm actually sorry, I'm a little worried about saying this is sodium bicarbonate. This might be sodium carbonate, and sodium bicarbonate is NaHCO3. Okay, so good to know. So that's why I'm going to from now on say Na2CO3 to avoid and then I'll figure out later what the right, okay, cool, what the right name is for this molecule. So, okay, so this carbonate ion is C double bond O bonded to two O's, and so it can get a -2 charge. Now, we might know, right, from the blood system that in the presence of water, the carbonic acid will or rather the carbonate will undergo the following reaction where it turns into a carbon. Okay, so this is merely saying the carbonate ion is presumably it's extremely basic. Okay, yep, okay, I think that's right. The carbonate is not an acidic salt, and neither is and okay, perfect. Excuse me. So, carbonate is not an acidic salt. Let's start here. Carbonic acid is an acid naturally, and the conjugate base is the carbonate ion. So if anything, carbonate is a basic salt. And it is, so let's knock out A. B, yes, sodium bicarbonate is neutral, but when it's put in the water, that dissociates. The answer D turns blue because sodium ions form sodium hydroxide in water. Well, presumably, actually, it would go the other way. Sodium hydroxide would turn into sodium ions because we know that sodium hydroxide is a strong base. That leaves us with C, because carbonate will react with water to disperse the charge. What is the maximum number of moles of nickel carbonate that can form during the precipitate reaction? So what is the rate limiting compound here? So we should figure out how many moles are here, how many moles are here, and whichever one is lower will be the limiting reagent, keeping in mind that there's 2 sodium ions and 1 nickel ion. Okay, is that right? There is 0.025 moles of nickel from this, from figuring, multiplying the mass times the molar mass, and then there's this amount, which will, okay, and we're not multiplying this by 2. At least in the answer choice, we're not. It seems as though that doesn't matter, meaning if we did multiply it by 2, indeed we would pick this. That's to say that these numbers are not random. They were picked so that they can match one another and the solution can neutralize. So this is a calculation question, and being able to multiply the mass times the molar mass to get the moles, and then comparing the moles is what needs to be done to see the limiting reagent to figure out the maximum number of moles which can be produced. According to the information in the passage, the gas that it evolves is carbon dioxide. Awesome. So is it sulfur dioxide, sulfur trioxide, carbon monoxide, or carbon dioxide? Let's see. We know what? we had a precipitate, which means we had a solid form. The solid went away once we added HCl, and a rapid evolution of a gas. So this is the gas that they're referring to, the rapid evolution of the gas. Well, presumably, the green precipitate is nickel carbonate. When the two are mixed together, the sulfate group will swap. So we have a double substitution reaction, if I recall correctly. In the first step. In the second step, the nickel with the CO3 Okay. The resulting slurry is sort of the question mark. We do two things to ascertain what's in that question mark. One thing we do is we add 6 molar of ammonia. That causes the solid again to disappear and a blue solution to form. Another thing we do separately, right, exclusively, is we add acid, and again the precipitate decreases and a gas evolves. What gas is it that evolves? When we add HCl into a mix with carbonic acid or CO3 minus carbonate ion, that will cause this carbon dioxide to form. And I would say this is the key thing that I did not know in this passage. So let me go through this in a bit of detail. CO3 2- is carbonate ion, and it's aqueous, which means it's in water, which means naturally, because of all the water around it, it will want to disperse its charge. The way in which it disperses its charge is by making HCO3- and hydroxide. That is a base. That means that this conjugate base is strong enough to produce so maybe this conjugate base is strong enough to produce another base. And this is a general fact. So anytime carbonate is in water, we'll have HCO3- and OH+. But what happens when we add HCl to this mix? Well, let's look at that hydroxide and the H. Assuming Cl will turn into a spectator ion, the hydrogen will link with the OH group, the H pluses will link with the OH minuses, and that net negative charge will be neutralized, which will increase the amount of H2O. Again, and I think I'm wrong in my reasoning, and I want to make that clear because it seems as though that would mean Le Chatelier's would drive the reaction to the left, meaning you would create more carbonate and water by adding HCl to the mix.